right. I know this has been a lot of me talking, way more than I like to, when it comes to notes, but this stuff gets a little tricky and a little picky. So I want to make sure that you are good with all of this. So limiting factors are all about the growth or the lack thereof within a population, right? The increase or decline of a population size. And it's the factors that affect the growth, right? So now what we're going to look at is when we look at a graph of populations changing, okay, we designate two different types of graphs, and that is an exponential and a logistic. So this is going to get really mathy for you, and hopefully you really already know these terms, and it's pretty fairly easy for you to understand. So we use graphs to look at population sizes and growth and declines over periods of time to help us understand the relationships that organisms share, right? So when we look at these graphs, which you're going to be looking at this week and working with this week, we have to understand what type of graph are they? What are they showing us? Okay, and then we have to analyze them to figure out what is going on within the interaction of those two organisms, or those two resources, or that organism and the resource, depending on whatever we're looking at. Okay, so to start us off, we're going to look at exponential growth. Okay, so exponential, as you probably should know, is all about increase or decrease pretty rapidly over a short period of time, right? So this happens in the abundance of resources. Okay, so when we're looking at populations, you're going to see exponential growth if there is abundant resources available, right? If I'm here in my house and I have a lot of boxes of Cheez-Its, right, I'm not going to die, okay? And if I'm a group of organisms, we're going to survive. We're going to survive this quarantine, and then our population may grow. Who knows, right? So if there's abundant resources, your population is always going to grow very rapidly. Okay, there's no limits on how large a population can grow when it comes to exponential growth. It can keep going on forever as long as there is enough resources. Okay, so on this graph, an exponential graph will always be a J curve. Okay, notice it's in a shape of a J. That's why it's called that. Okay, and it's short term. Okay, remember, it's really quickly. Okay, so if I'm a deer population and there's a massive field of grass, okay, they're going to eat all that grass and their population is going to skyrocket. But guess what? Eventually that grass is going to run out. So that population is then going to decrease, right? So that's why it's only short term, because these resources can't last forever. Okay, it can only last to a certain point, which is what we're going to talk about here in just a minute. So the next type of graph you're going to see is what we call a logistic growth graph. Okay, this is in the presence of limiting factors, population growth slows. Okay, so back to our limiting factor terms. Okay, so a population will grow quickly until it reaches the environment's carrying capacity. We're going to explain that here in just a second. But look at this graph. It originally starts exponential, right? Now, a true exponential graph would show that this population just keeps on growing, right, until it stops, right? It can just keep going, okay, because it's got all the abundance of resources. But a logistic graph is different because, look, it levels out, okay, or it decreases and kind of goes along this path, okay? So it's more of an S-curve shape as opposed to a J, okay? So it starts as a J, but then it levels off, okay? And that's all because of this idea of a carrying capacity, okay? Logistic graphs or logistic growth graphs are generally going to be looking at long-term, okay, where, remember, again, exponential looks at short-term, okay? So let's look at this idea of carrying capacity. Carrying capacity, honestly, is one of the biggest terms that you're going to need to know out of this week, as far as what that is, how it affects populations, and those populations growing. Okay, so carrying capacity is the maximum number of individuals a given area can support. Okay, so within an area, every place in this world has a maximum number, right? Think of this as being when you go to a restaurant, right? And on the door at the restaurant, there's always a sign and it says capacity, right? And it has a number. That is the number of people that can fit in that restaurant safely. Okay. Carrying capacity is the same thing in the natural world, right? Where it's the maximum number of individuals that an area can support based on the resources available. Okay. So if we go look out at the field, out behind Liberty North, there's only a certain amount of grass to support organisms, right? So there's a number that you could give called the carrying capacity that would say this area can only support this number of deer. Okay. So when populations exceed their carrying capacity, organisms must die or leave the area. Okay. So when we look at these logistic growth curves, populations are growing because you have resources, but guess what? Now you run out of them. So either some of your population has to die or they have to leave. So what do you see the population do? You see it decrease, right? Then you get below the carrying capacity, and now you have less organisms than the number that this area can support. So guess what the population is going to do? It's going to grow until it reaches that carrying capacity again. Then something's got to change, right? Someone's got to die or someone's got to leave. So then you die and the population drops below the carrying capacity, and then eventually it's going to increase over the carrying capacity, and it's this constant roller coaster of events, right? And so when we look at these graphs, we want to look at what is the carrying capacity. We can look at a graph and say, based on these peaks and valleys, we can say the carrying capacity is right in the middle, right? Because all of these overshoots, okay, all these arches, those designate when they've gone over, and then they have to die, right? They have to drop. So that's the carrying capacity line in this graph. Okay, so how does carrying capacity change? Okay, so with abiotic factors, these are non-living things, okay? Things like amount of available sunlight, amount of water, temperature, okay? Those would all be abiotic factors, okay? This will change the carrying capacity of an environment, okay? So think about it. If this room can fit 10 people, okay, let's say that, okay? This room has a carrying capacity of 10 people, all right? If, let's say I have a well over here of water, right? That water can only support 10 people, okay? But what if the well dries up and now I only have the amount of water to support 5 people? Does that change the carrying capacity? Absolutely it does, right? Now the carrying capacity is 5, not 10, because it's all about the water that's available to keep us alive, right? If we're talking out in the natural world, sunlight, okay, could be a factor that affects the carrying capacity based on if plants are growing, right? If there's no sunlight and the plants don't grow, can that change how many deer that area can support? Absolutely it can, okay? So then we look at biotic factors. So these are living things. These are disease, competition, parasitism, okay? These things will never change the carrying capacity. The carrying capacity can only be changed by abiotic factors, okay? Because think about it. Living things like disease, competition, parasitism. So let's say disease. If I have 10 people in this room, and that's the carrying capacity, and one of us gets COVID, okay, all of us get COVID, but can this room still support 10 people? Yes, it changes nothing about the resources available in this room, okay? Let's say with competition, okay, if the field behind Liberty North can support 20 deer and it can support, let's say, 20 rabbits, the competition between those two things has nothing to do with the resources available of how many organisms it can support, right? If it can support 20 of each, that's the carrying capacity. It's not going to change, okay? So again, biotic factors will not change the carrying capacity. Abiotic factors will. Okay? So in this week, what you're really going to look at is relationships between organisms and how those relationships affect the populations of these organisms. Okay, I'm going to pull up your assignment here real quick. So this is going to be your assignment for the week. There's three parts, I believe. It's a little extensive. You'll have all week to complete this. The first part is looking at this table, reading this little blurb about Deer Island. Okay, this is going to look at predator-prey relationships and how that affects a population. Okay, so the first thing you'll have to do in this is do a little bit of math. It explains it right here in this section here, but you're going to have to fill out this column. Okay, to do that, you're going to take the number of deer being born minus the deer dying. Okay, and what that's going to show us is how is the population changing, right? So we have some wolves and some deer. Okay, and these are the deer being born. Deer predation, these are the deer being eaten. These are the deer that are starving to death. Okay, so to find the population change, you're going to take these two, add them together, and subtract it from this number. So 800 minus 500, that gives you a positive increase of 3, right? So all of these will either start with a plus or minus. Okay, so on this one, let's see, we have 920. Oh boy, this is going to make me do some quick math. Not good for me. So we have 920, and then we have 480 plus 240, so that's going to be 720, right? So 920 minus 720, that's going to give us an increase of 200, right? So some of these are going to end up being minus if the number of dead deer is greater than the number of born deer, okay? So keep that in mind as you work through that. All right, so on the rest of this assignment, you really shouldn't have to input anything other than answers and thought. So you're going to use this graph, you're going to use this data table and look at it along with the graph. Okay, so this is the graph for this data table. Okay, and then these questions here, this graph analysis is going to be answered based on this graph here. Okay. Then you have part 2, okay, which is a carrying capacity simulation, kind of looking at how the carrying capacity affects population growth. And so with that, you're going to be using this data table and this graph, the plateau deer population graph, to answer these graph analysis questions down here. Okay. So it looks like there's only 2 parts. Sorry, I told you there was 3. Only 2 parts. That will be our assignment for the week. Okay, so watch these 3 videos and then complete this, and that will be your task for the week. Make sure you email me with any questions. Otherwise, have a wonderful, wonderful week. Feel free to drop in our lunchtime chat. I know there's some days that I'm able to be there all the time. There's some days like today that I'm not. I got meetings left and right all over the place. So just make sure you email me if you want to chat. I'm all for it. Otherwise, have a wonderful week. Take care of yourself. See ya.